Hello and welcome back to this online short course by Red Dot Analytics, Survival Analysis, an Introduction to Concepts, Methods and Software. In the previous section, we spoke about proportional hazards, what this meant, and how we can test for this assumption. And in this section, we'll speak about allowing for non-proportional hazards. So what do we do when the proportional hazards assumption is violated? Well, one option would be to include interactions between time and the variable where the violation has occurred. Another option would to be run analysis in separate subgroups for the variable where we see a violation of the proportional hazards assumption. In this way, you would essentially allow for interactions between every variable in your model and the variable that shows non-proportionality. Another option would to be fit a stratified Cox model. Now, this allows for separate baseline hazards for the levels of the variable that we see non-proportional hazards for. But since the baseline hazard is not actually estimated in Cox models, this should only be used for nuisance variables, so variables that we're not actually interested in quantifying the effect of. And this is what a stratified Cox model looks like. Again, it's very similar to the standard survival analysis regression model. But the thing that differs here is this N, which you can see that here we would have a baseline hazard, this lambda naught, which is specific to levels of our variable N. But we actually get one estimate of our beta's hazard ratio. So if we were talking about grade, as we spoke about in the previous section, where we saw that there was a non-proportional effect of grade, then we would, in the background, what's going on is that the Cox model would fit two separate baseline hazard functions for those that had grade 3 and those that didn't. We wouldn't know what they were. They could vary freely, but this would allow for the facts that this would allow for this non-proportionality, but we would still get an estimate of hormonal therapy that would be just one value, or the hazard ratio for hormonal therapy we would just get one. So in these examples, we'll focus on the effect of grade because that's the variable that we saw where we had the most problems with non-proportionality in our example. And we're going to relax the proportional hazards assumption for grade, this means. So one way to start by allowing for non-proportional hazards is to make sure that we have a variable in our data set which represents the time scale. So what we're going to do is we're going to go to Stata and use the st-split command to again split up our data set based on specific time periods. And we'll focus on splitting our time scale up into 3 periods: 0 to 2 years after breast cancer diagnosis, 2 to 5 years after breast cancer diagnosis, and 5+ years after breast cancer diagnosis. Note that we have follow-up until just after 7 years after breast cancer diagnosis. So we've been through this before, but let's just go over this again, just so you're sure about what our data set looks like when we use st-split. So previously, our data set has looked something like this. So if we just list some of our variables in our data set for the first 10 observations, we would see something that looks like this, where we have ID variables 1 to 10, indicating that the first 10 observations are for unique individuals. And we follow individuals from 0 T0, which is created in the st-set command earlier on that we presented. Follow everyone from time 0, which is their time of breast cancer diagnosis, until _T, which is the time at which they have their event, _D, which is 1 if it's the event of interest and 0 otherwise. And we can see for the first individual, say we follow them from breast cancer diagnosis until 4.97 years, at which point they either die or have a recurrence of breast cancer. Now, if we use the st-split command and create a variable representing the follow-up, fu, then we can do this using the command here, st-split, and then we write the variable name we want to create. And then we say at which time points do we want to split this variable at. So we're going to split it 0 to 2 years, 2 to 5 years, and then 5 to the end of follow-up, and end of follow-up is around 7 point something years here. So we've said 8 years. And then we can look at our variables again and include this variable FU, which is the one that we created using the stsplit command, to see what happens. So now what should be really clear is that we actually have multiple rows per individual, because we no longer have 1 to 10 ID variable here for the first 10 observations. If we look at the first 2 lines observations, we can see that these correspond to the first individual with ID 1. Our hormone and our age variables are exactly the same because these are time fixed. These are time variables at the time at the start of follow-up at diagnosis. And then you can see that we have a follow-up of 0, which goes from 0 to 2 years, at which point this individual did not have an event. And then on the second row for ID1, we follow them in the second category of follow-up from 2 to 4.97 years, at which point they did have an event of interest. So they either had a breast cancer reoccurrence or death. So you can see that we are creating more observations than our data set representing these time slots. And we can also, if we want to, summarize the time variable by our new variable to see that we have split 2 and 5 years. So we can see here that if we use the BySort FU command and then say summarize underscore T, we say summarize the underscore T variable within levels of the FU variable. Then we can see that for when FU is equal to 0, we are looking at between 0 and 2 years of follow-up. If we look at FU is equal to 2, this is when we follow from 2 to 5 years. And then FU is equal to 5 follows individuals from 5 to a maximum of 7.28 years. So the values that FU takes, 0, 2, and 5, represent the left-hand side of those time intervals. So one thing that we can do by follow-up time is we can estimate the crude rate of recurrence or death in each of these time periods and by grade of cancer. And we can do this using the SDRate command, which we've used previously, and just tell Stata that we're interested in looking at these 2 variables, FU and grade 3. We use the per 100 option, which tells Stata we are interested in looking at rates per 100 person years. And years here because we have our time scale specified in years, which was specified in the SDSet command. So we would get out some values such as this, where really what we're interested in is looking at these rates. I'll just go through again what everything is. So the FU represents our FU variable, which is 0, 2, and 5. We have grade, which is 0 or 1. The D variable tells you how many events we have had within each of these groups, and the Y is the person time at risk here per 100 person years. And then the rate is just the number of events divided by the person time at risk. So what we can see is that within the first 2 years, when we have grades not equal to 3, then the rate is 11.58 per 100 person years of reoccurrence or death. And if we look at the rate within those that had a grade 3 cancer within this time period of 0 to 2 years, the rate is 22.54. So we see a really large difference there between the 2 values. If we look within the next time period, when follow-up is 2 to 5 years, so represented by this FU is equal to 2, we can see that there's still a difference between the grade groups, but it's much less pronounced, with 14.67 and 12.39 per 100 person years. And again, for the last period, we see that there's some difference, but not as large. So it looks like that there's quite a large difference early on between these 2 grade categories, and later on this may not be as different across our timescale. So let's look at fitting a piecewise exponential model that assumes non-proportionality. So what we're going to do is we're going to include an interaction between our FU variable and grade variable to relax this proportional hazard assumption in this piecewise exponential model. And what we do is we use our sdreg command in Stata. This tells Stata that we want to fit an exponential model along with this option distexp. And then we include our exposure of interest or hormonal therapy. Grade here, which is interacted with our variable FU. So we allow for the main effects and the interaction between these two because we have this double hash here. And then we can also include H category in this variable. And we have this no log and no header options here just for display options. And then this is the output that we get. We can see that we have a hazard ratio for our exposure of interest hormonal therapy, which is 0.67. Remember that this hasn't been interacted with time, so this hazard ratio is constant across the whole of our time scale. And then we have a main effect of the grade variable, and we have the main effect of the follow-up variable. But we also include this interaction variable here. And we have the age category variable and the constant variable, which represents the baseline hazard when everything else in the model is equal to 0. So what we've done by this is we've allowed the hazard ratio to vary across our timescale with 3 different hazard ratios for the rate of recurrence of death or recurrence of breast cancer in grade 3 cancer versus no grade 3 cancer in the first 2 years, in the first 2 to 5 years, and greater than 5 years after diagnosis. And what this looks like is something like this. When we predict from our model, we see a hazard ratio that changes in these different time periods for grade. So now we're focusing not on our hormonal therapy, we're focusing on grade, where we've allowed the hazard ratio to change over time. And we see that the hazard ratio is just under 2 from between 0 to 2 years after diagnosis. We see that it's 0.5 between 2 and 5 years. And then we see that it is around 0.01, let's say 0.1 between 5 and 7.3 years. So instead of making the assumption that the hazard ratio is constant over time, as we did previously, even when fitting a piecewise exponential model and allowing for the rates to change over time, we now allow the rates to change across these time slots, but we also allow the hazard ratio of grade to change across the time slots. So what we can do to test for the inclusion of the interaction term and a test of non-proportionality of grade that we presented in the previous section is we can perform a likelihood ratio test. So how we would do that is we would start by fitting a model that does not include an interaction. Here the quietly option, or qui, which stands for quietly, just tells Stata not to display the output of the command. And then we use this estimate store option or command to say, let's save the values of this model in this we're going to call it model 1. And then we do the same thing for the model with the interaction, where you can see here we have the double hash notation to say that we want to include main effects and interactions between grade and FU. And then we include this estimate store again to say, let's save these estimates in this thing we're going to call model 2. And we use the LR test command to say, compare model 1 to model 2 by this likelihood ratio test. And what we get overall is we get a p-value of 0.01, which indicates that we see a significant improvement in our model when including this interaction, and thus indicating that we should allow for non-proportionality of grade. So our test is significant, indicating that we should include the interaction term and thus relax the proportional hazards assumption. So we can also model non-proportionality using a Cox model, and we can do this whilst relaxing the proportional hazards of grade in a very similar way. By including this interaction term. and we get a very similar output. As I said, we get very similar estimates of the hazard ratio when using the piecewise exponential model as the non-proportional Cox model. And you can see here what this looks like. You can see there's a little bit of variation between the estimates here. This is the hazard ratio for grade 3 versus 1 to 2 over time since breast cancer diagnosis. The blue line represents the exponential, the piecewise exponential model, and the orange line represents the Cox. So we can see that there is a little bit of variation here, but we can also see that this does vary across these. Both of them allow for non-proportionality because the hazard ratio changes across the timescale. So another option, if you want to fit a non-proportional Cox model, is to use the TVC and the TExp options of the ST-Cox command. So note here in this example, we're only going to allow the hazard ratio to change after 2 years instead of having 3 different time slots. So how we do that is we specify ST-Cox. We want to fit a Cox model here. We fit our variables in the model, and then we use this option TVC to say which variable do we want to allow for non-proportional hazards, and that's grade 3. And then we use this TExp option to tell Stata where do we want the split to be on the time scale. Well, we want it to be when _t is greater than or equal to 2. So we're going to allow the hazard ratio to change after 2 years. So we'll have one hazard ratio prior to 2 years and one after 2 years. And then we get the output here, which shows you what the hazard ratios are for hormonal therapy, which is constant across time. This is 0.67. So we see very similar estimate of the hazard ratio from all of these models. In fact, it's varied from 0.67 to 0.770, I think. We get an effect of grade 3 before 2 years at 1.93. And then we also get the age category effects. And we see the hazard ratio after 2 years. And then the last option is to run a stratified Cox model, which allows for a different baseline hazard function for the strata variable. So this can be used when we wish to remove a problematic variable that violates the proportional hazards assumption. We will not get any estimates for the effect of the stratum variable on the hazard rate or hazard ratios. Here, we will not get any hazard ratio estimate for the effect of grade on the recurrence or death rate. So what we do is we use the strata option of the ST-Cox command in Stata to fit a stratified Cox model. It looks something like this. So we have a similar command to what we've used before, ST-Cox for the Cox model. We have our exposure of interest hormone. We have our age category, and we don't have grade, but we have grade included in this strata option here to say we want to fit a stratified Cox model using grade 3 as a strata. And then the outcome looks like this. We can see here that we have an estimate of our hazard ratio for our exposure, hormonal therapy. We have estimates for our age categories, the hazard ratios compared to the lowest age category, but we don't see any output from the grade variable, which is not surprising because we have this as our strata variable, and you can see here that it states that in the output, strata variable is grade 3. So what it's doing in the background is allowing for the non-proportionality of grade 3, but we don't get any estimate from that. We don't know what the effect of grade 3 is on the rate of reoccurrence and death of breast cancer. So that was everything for how to fit non-proportional hazards models. Here's some references if you're interested in reading some more about this. This was the last section apart from the summary, so I will see you in the next section where we summarize what we've learned in this course.